Good evening and welcome to Tinkering with Edkelar. It is time for a bit more test equipment again. For this episode I got an HP 3488A. It is called a switch control unit. There is a slash between the switch and control word, but I'm pretty sure that the unit is controlling switches. Other manufacturers might be calling this a scanner. Many names, but just how did I end up with it? Well, after some of my devices came with GPIB, I was hunting for some matching gear to complement them and make a useful, something at least. And this one came up during a search for GPIB. After looking into it, I just had to have it. And what does it do? The main purpose of HPIB or GPIB is to automate measurements. You wire up something and then a control computer runs through a script to repeat some task over and over again. In the industry, this might be used for production line testing. No use for me at all. But what if you want to run something over a longer period and check if it behaves over time? Like, for example, check the discharge or charge behavior of a battery? That might come in handy. Now, quite a few of these automations require several meters at a time, and even for a big corporation, getting a dozen or so premium GPIB-enabled multimeters would be a major cost factor. This is where switching units or scanners come in. These are essentially a set of switches that can be connected to the test setup to switch one lab device into various positions on the component under test. Usually, these are relay-based, so the setup is floating and can switch in and out random signals. The strength of this device in particular, it uses up to 5 modules, like this one, so there are multiple switching options and configurations available in the same device. Now, let's have a peek. The base unit is almost completely empty. And without any modules, nothing is going to happen either. The front panel is a bit dirty and the case is quite a bit sticky all over. Might be some sort of residue, smoke residue maybe. Brrr. Getting in seemed easy at first. Remove the rack mount hardware and the 6 screws in the bottom end. But somehow the case was stuck at first and took quite a bit of prying. As mentioned before, the inside is mostly air, or rather the slots for the actual switching modules. There is a backplane with the appropriate connectors, a power supply unit next to a transformer, which is the only source of gravity in here, and the controller, which takes up the space of one module. Thus, we end up with 5 slots available. I think HP had a parallel model of this with about double the slots. Taking apart the unit took a bit of time. Some screws are hidden behind others. Namely, the power supply needed to come out before you can access the screws that hold the center card holder. The power wire is held down with some cable ties. These should pop open, but they were too sticky and they bent and stretched all over. So, off they go. The front panel PCB is heat staked. I'll try to melt them this time. Maybe I can restake them later. Giving everything a good scrub in the sink. Up next, cleaning the power switch. Again with the weird one that needs a complete dissection. Whoops! That plastic is brittle. And after a bit of contact cleaner, assembling it again. Adding a bit of super glue to fix that cover. The voltage selection switch is next. It looks like a common version I have seen many times before. But it isn't. It's yet another style of switch. This one has the contacts on the side. Sheesh, how many different switch types does the industry need? This is going to be fun. And indeed it was. Tweaking the contacts in between the outer shell and the slider took quite a bit of bleeping. While I got the power connector desoldered, I drilled out the rivets and replaced the input lines filter with a new one. These go up in a poof of nasty smoke if they age. Since I don't have matching rivets, I'm using a set of M3 screws to mount the new one. Looks close to the original and works. And a bit of heat shrink tube for insulation. Now, recapping. I looked at all the caps, but as far as I can tell, it's only using the good tantalum ones. The only regular electrolytic is the main power supply one, and that is a rather specific form factor that might get expensive. So, better try to avoid changing that if we can. I desoldered it, both to check for goo underneath and to hook it up to some DC to confirm. Not leaking either way. Good. The construction of the power supply is a bit odd. There is a regular transformer, but also what appears to be a DC to DC converter. Why not use a switch mode supply to begin with at this point? Strange. Starting to assemble everything. The transformer is first. and the voltage selection switch, which is located inside the unit. Then the power switch. And I realized that the power wires needs to be routed on the outside. The controller card goes in next. For the front panel, I had two RTFM. Two of the keypads are the same form factor, so better make sure that the keys end up in the right location. For starters, I just push the panel in place against the PCB. And give it a try. Checking the power supply output without the load first, just to make sure that there is no problem here. Okay, 5-ish volts. Check. And power on. Yay, I see something on the display. Is that? Yes! HP seemed to love their lazy T. It's in use on the 9825 as an input prompt, and again here to indicate a normal, idle state. Let's see, there's a test button on it. Yes, that looks promising. After trying out a few buttons, I commit to the front panel by staking the plastic shut again. and adding the frame into the lower clamshell again. It's a bit on the fiddly side, since the power switch needs to poke through the front panel, and that is just sitting in a notch in the shell. So the heavy frame and the flimsy front panel have to be inserted at the same time, both of which bind up quite easily. Now you might be asking yourself, how would one switch anything without any module? I asked myself the same question, and so I splurged a bit. Note that these modules are around on eBay for various price ranges, so be sure to compare. The cheaper offers are around $100, the more ridiculous ones go well beyond $600 per card. Holy sticker shock. There is even a breadboard prototyping one around, new old stock, for over $1,000. Yikes! So, let's remove the shielding tins and give them all a good scrub. You notice that there are different types of modules. My goal was to get 2 of each to have a reasonable selection for whatever I might need it for. Before I close the shielding tins again, I'll do a quick check of each module. These are test gear and need to be up and running when called for. Adding a faulty module to an experiment can cost lots of time troubleshooting in the wrong direction. First off, I got a set of 44478B modules. These are BNC based switches with a 1 out of 4 topology. So you have 2 groups with a center connector each and can route them to one of the other 4 connections. These cards go up to 1.3 GHz, plenty of room, but I only got the B version, which is the 75 ohm one. The A version would be the 50 ohm one. The channels can be controlled via the front panel. Close and open can switch a connection on or off. They are used by providing the address of the switch in question. That is a 3-digit number starting with the slot number 125 and then the number of the contact on the card. These 2 digits depend on the card. For this one, it's 0 or 1 for the 2 blocks and then 0 to 3 for the 4 connectors. Whenever you close a contact, any other contacts that are incompatible with the new selection are opened before that. And here I ran into a problem too. The first channel on one of the cards didn't switch into anything but the first connector. I can hear the relays clicking, but the signal is lost. As you can see here, the topology has a parking position for unused connectors. These are the golden plugs on the card and allow for termination resistors to be added. So unused inputs can be parked with proper termination if needed. That's why there are so many relays on it. But the problem turns out to be in the 3 actual routing relays. Those only ever switch back to the normal position. They don't switch over at all. None of them. There must be a fault in the controlling circuitry, but try as I might, I could not find a schematic diagram of these cards. I did poke around quite a bit, but apart from seeing that the control pulse was sometimes clipped at 2 volts instead of 5, I couldn't see anything wrong. I changed the transistor that was sus and a diode that had a chipped edge. Still, no change. These are latching relays. When I manually trigger them, with the card outside the unit of course, the signal path does work for all 4 connections. But for some reason, there is something blocking the signal switching over inside the unit. I'm running out of time, so this card goes onto the to be fixed pile. Now while I have my scope and signal generator set up, let's move on to the 44472A card. It is the same switching style as the previous one, but only up to 50 MHz. So let's go over it. For these cards, one of them had a broken PNC connector when it arrived. Must have taken a bump in transit somewhere. I did find an exact match for a replacement. Here, both cards work fine. Next. Here's a relay card, model number 44470A. Since these cards came with the base unit, I got 3 of those. The circuitry is a 1 to 10 multiplexer with 2 wires in parallel, so you can connect one pair of sockets to any of the other 10 at any time. And the contacts are closing and opening. They provide decent continuity. Next. This one looks incredibly close to the previous one, but it is set up very much differently. It's model 44471A, a generic relay card. The closing relay contacts are just made available to the outside world. Nothing special. So 10 closing contacts for this one. And of course all the contacts are fine as well. Next. Another relay card. But oddly enough, this one only has 7 relays populated. Model number 44477A. Strange design indeed. This one is also a generic relay card, but it does provide both ends of the relays, so you can toggle something with them. Also checks out okay. Next. This one is called a 4x4 relay matrix, model number 44473A. It provides 4 rows and 4 columns of paired wires. The relays can switch in any connection point between the rows and columns. Neat! Checks out too! Next! Finally, this one here is called a digital I/O module, model number 44474A. It has 16 digital channels, which can be either input or output, depending on the configuration, and a few control lines too. With this, you can pretty much remote control any non-GPIB equipment or provide digital test signals as an input. I can't fully validate all the channels and options for this, I'd be sitting in here for days. But in the standard mode, the output is also read back as an input as well. So writing bits should reflect on the input side. Works. After testing all the modules and only having one for repair in the pile, I fit all the shielding tins again. Now, the next question that should have come up by now: how does one connect to the cards? And the answer is, with even more money. Other than the BNC based cards, all of them have these custom connectors on the rear. After inserting the card and snapping it into place with the pull handles, you can add these connector blocks. The idea here is that different test setups can keep these connectors attached, and so when you need to change over to another product, you just pop in the required cards, connect the new test rig, and start over. Sadly, these connectors are usually sold separately, and also for quite a bit of money. Prices here range from $60 to, again, well over $300. Again, yikes! The main problem with these is that they are keyed for specific card types, so you don't connect the wrong lines by accident. That could be fixed, but the connector terminals also have labels printed on them, so you know what wire goes into which hole. So better get the correct matching block. For me, only 4 of my cards came with these blocks: the digital ones and the matrix relay ones. What's a bit unusual is the connection PCB that sticks out and has a D-sub connector on it. That's not factory. But for the digital ones, I kind of like the idea and will keep it. For the relay ones, let's get rid of it. You can see here how you actually connect your own wiring to the screw terminals. And finally, the biggest test of them all: GPIB. Cross your claws. It works! Ha! Conveniently, almost all the commands are the same on the front panel and the GPIB interface. And that concludes this episode. Let's see what we can... Now, wait a second. I couldn't just let the broken card be broken, could I? After finishing the script for this episode, I sat down again and went over it. Did some measurements too. This is the control voltage across the relay, 1 trace for each side. So as long as both are at the same level, the relay stays where it is. If they have opposite polarity, it will switch to whatever side is called for, depending on which end is positive. To control this, HP made the following rough circuit: an NPN transistor to positive, a pull-down driver chip on the negative side, and a pair of diodes in one leg. The transistor that controls the offending 3 relay coils on the left side was measuring weird and I replaced it. Didn't change much, but it gave me these measurements. It seems that the yellow trace isn't quite getting enough oomph when it should pull high. So I decided to get another transistor with a significantly higher beta value, and lo and behold, it switches! Woohoo! Didn't expect this to be an issue with this circuit, but it clearly was. And that concludes this episode. Let's see when this nifty piece of equipment will become useful. I hope you enjoyed this little instrumentation installment. See you next time! I did find an exact replacement for a match. Yes, I did find a replacement for a match. Of course I did. And that concludes this episode. Let's see what we can...